Now let's talk about what are the data structures which are used to keep track of the free spaces and the occupied spaces when you go for dynamic allocation, right? So now the problem is this: we have main memory here, this is the operating system, and this is user space, and say we have got 4 processes initially, and 4 processes are occupying the memory like this, right? One process, and then second process, and then third process, and we have given the memory in such a way that there is no internal fragmentation and there is no wastage as of now. So initially when we do this, it will be beautiful, everything will be very good. In the sense, there will be no internal fragmentation, there will be no external fragmentation, and whenever there is space, that space will be at the end, right? But over a period of time, as the algorithm progresses or this method progresses, there will be lots of holes created, and managing them is going to be very, is a very headache. So what are the various data structures which we are going to use is, let us assume that here the size of this is 2 MB, the process, and here the size of it is 4 MB and 4 MB and say 2 MB again, right? So this is how the process are there, right? And now what I'll try to do is assume that suddenly this 2 MB vanished, which means the 2 MB has this process which occupied 2 MB got finished, and therefore it is pulled back. And now again this 2 MB also got finished, completed, therefore it is pulled back. Now we have to keep track of what are the free spaces now, so that later they can be assigned to various processes, right? So let us say this is process P1 is present here and process P2 is present here, and this is a hole and this is a hole. Now we have 2 holes and 2 processes, and therefore next time when anyone asks me for a memory, I am going to find the free hole and I am going to allocate to that, right? So how am I going to maintain what are all the free spaces and what are all the occupied spaces? See, in case of static partitioning or fixed partitioning, it is very easy, because there are only fixed number of partitions, and we could have declared an array, and that array is going to say which one is what, freed or occupied, if it is process or hole. But now here the holes will get created dynamically and they will get vanished dynamically, and more holes will be created over a period of time, and it is going to be complex then, right? So one basic data structure which is used for this is called as bitmap. So there are 2 data structures which are used. One is bitmap and other is linked list. So now let's talk about bitmap first. So bitmap is used to keep track of all the empty spaces or the free holes in case of dynamic allocation, right? So this bitmap concept is this. So they will try, let us say this is the memory. I'm just writing the memory as a one-dimensional array, and it is true that memory is a one-dimensional array. Having that kind of conceptual view is okay, and this kind of conceptual view is also okay. It is a one-dimensional array. Now what I try to do is, I'll try to divide the memory into various small parts, which are also called as allocation units. So they are called as allocation units, which means I'm going to divide the memory like this, allocation units. Allocation units. Okay, so an allocation unit can be anything that you decide. You might say that according to you the allocation unit is 4 bytes, or you may say that according to you your allocation byte is 10 bytes. So whatever you decide upon, that is going to be allocation unit, right? And now that memory, when it is partitioned into allocation units like this, let us say I'm partitioning the allocation units into I'm deciding that my allocation unit is 4 bytes each. Then what happens is, this entire thing can be divided into many 4 bytes, isn't it? Many 4 bytes like this. The entire memory is divided into many 4 bytes of allocation units, right? And now when I represent this entire memory like this, then there will be contiguously some allocation bytes which will be empty, right? Let us say allocation bytes are like this, right? And accordingly, let us say here there is a hole, all these allocation bytes are free, and there is hole, and then here there is a process, and again here there is a hole, and again here there is a process, right? Then what I try to do is, for every allocation unit I'll try to assign a bit, and that bit is going to contain 0 if that allocation hole is present as a part of the whole, and if that bit is 1, it means that it is occupied by a process, right? Then what I say is, what is that I'm trying to say is, I'm going to have an array of bits, and now each bit in this is going to represent one allocation, right? One allocation unit. Watch it. Now each bit is pointing to one allocation unit, right? Like that. And the number of bits will be equal to the number of allocation units we have, right? Okay, I think it is going to take a lot of time writing it. Fine, done. Now see this. Whatever allocation unit, whatever bits are representing free spaces or holes, there I am going to put 0, which means, see this entire part, it is completely going to be a hole, therefore all these allocation units are going to be zeros. So 0, 0, 0, 0, right? And this part from here to here is representing a occupied, it is representing that it is occupied by a process, therefore 1, 1, 1, 1, right? And again two allocation blocks are holes, therefore 0, 0, and again 2 allocation blocks are occupied, 1, 1, right? Therefore by using this list of zeros and ones, we can find out what part of memory is occupied and what part of memory is free, right? Which means holes. Got it? Now what is the problem with this method is, one thing is, depending on the size of your allocation unit, right, our bitmap size is going to depend. Let us say, what is the best allocation sizes? Okay, let's talk about it. Let's say I am deciding that my allocation unit size is 1 bit, which means for every 1 bit I am maintaining a bit in the list, in this bitmap, saying whether it is free or not. Then what happens? For half of the bits I need to if the memory is totally M, right, or 1 by 2 of the memory, half of the memory will be wasted for the bitmap, isn't it? So if the allocation unit is going to be 4 bytes, see, it is somewhat difficult to understand, try to understand it. If the allocation unit is going to be 4 bytes, which means 4 bytes is nothing but 32 bits. So what does it mean? For every 32 bits, I am going to have 1 bit representing whether it is free or occupied, right? So bitmap is going to take 1 by 32 plus 1, which is nothing but 1 by 33rd part of your total memory is going to be taken up by the bitmap, isn't it? Why? Because for every 32 bits, if your allocation unit size is going to be 4 bytes, then in order to say that these 4 bytes are free or not, we are going to represent it with 1 bit, right? Which means for every 32 bits, I am going to use 1 bit to represent it, whether it is free or empty, right? Therefore 1 by 33rd of the memory is going to be taken up by the bitmap. Fine. So if you try to increase it, which means if you try to increase the size of your allocation unit, then definitely the size of the bitmap is going to be decreased. But then there is a disadvantage there. Can you just guess what could be the disadvantage? So the disadvantage here is like this. Let us say a process is actually, you are seeing that process is starting from here, from this part to this part, you are seeing that the process is present, isn't it? There is but then the problem is, even though the process is present from this part to this part, maybe it has taken up from the first of half, and in the last one it has taken up half of it, which means even though it is saying that the process has taken up 1, 2, 3, 4 allocation units, but it might so happen that it has used only half of the first allocation unit and only half of the last allocation unit, right? And we are not able to represent the half of the first allocation unit is idle, because we are going to use a bit to either say it is occupied or not. We are not having any bits to say it is half occupied or full occupied, right? Therefore, depending on the granularity of your allocation unit, the size of the allocation unit, the bitmap size is going to depend on that. But if you decrease the size of the granularity unit, that allocation unit, it is going to give you better in terms of the memory utilization, right? Because you are not going to waste a lot of space, like this, by wasting half of the granularity units. But then that is going to lead to a very big bitmap size. So in order to decrease the bitmap size, you have to increase the sizes of allocation units. But then if you do that, it is going to waste up a lot of space. It is like this. There is no way you can either increase the size. I mean, you have to come up with a fixed size. I mean, some good size. So people say that 4 bytes is a good size and dedicating 1 by 33rd is better, right? Okay, fine. Let's say we have dedicated some memory and we are not concerned about the memory wastage. Even though you are not concerned about the memory wastage, the main problem lies in how are you going to find a hole, right? So now a hole is nothing but an array of, or a run of zeros, isn't it? So wherever you get a contiguous run of zeros, that is nothing but a hole. Now whenever you want to allocate memory to a process, what are you supposed to find out is the hole which is large enough to hold the process. But then in order to find out a hole, we have to scan the entire bitmap and then see where there is a run of zeros, which is going to be complex and the algorithm is going to be slow. So finding out a run of zeros, run of zero means run of zero means all zeros, right? So finding out a run of zeros in the bitmap in order to find out a hole which you want to allocate is going to take up more time. Therefore, the disadvantage of this method is not just the memory that is required to keep track of all the holes, this bitmap. The second disadvantage is the finding out a hole is going to be a problem, right? And anyway, it has got some advantages too. One advantage is, in case if one of the process gets freed up, let us say this process got freed up, right? Then you have to just simply make all these ones as zeros, isn't it? Therefore, you need not worry about concatenating two holes adjacent to it. They will automatically get concatenated, isn't it? So whenever any process gets freed up, it will automatically get merged with the hole which is adjacent to it. You need not do anything, right? So it has got advantages and disadvantages, but it is not widely popular because over a period of time, over a period of time, the holes are going to be very large, and then number of zeros and ones overlapping. That number of zeros and ones, finding the run of zeros is going to be difficult. So it has been used long back, but recently no one is really using it, right? And the next method, which is very widely popular when this contiguous allocation with the dynamic partitioning was there, is linked list. So linked list has got some advantages compared to this bitmap, and it too has got some disadvantages, but which are actually easy to fix up, right? So bitmap is not widely used, so right now we are not using it nowhere. But then linked list is actually used, and right now there are very few systems which are using it, but anyway we shall see it. Okay, fine.